What I'd like to do is go over a few examples that really follow from the Rank Nullity Theorem, and they're examples of how to use it. This is a powerful theorem in linear algebra, and I will remind us what it says right now. So when you have a matrix A, that is n by m, that says n rows and m columns, then the dimension of the kernel of A plus the dimension of the image of A is m, and this is the number of columns. That is an important observation. Okay. Now, restated, well, the dimension of the kernel is called the nullity. That is something we discussed of the matrix. And plus, now we know the dimension of the image. This is the rank of the matrix because, for example, every leading one in the reduced row echelon form corresponds to an element in the basis for the image. You pull off that corresponding column in your matrix. Okay, so this says the nullity plus the rank is the number of columns. This is what the rank nullity theorem says. Okay, now let's use it in a few examples. The first one is a question. Can we have a 4x3 matrix A and a 3x4 matrix B such that A times B is the 4x4 identity? Certainly, just multiplying 4x3 and 3x4 will give us a 4x4 matrix. But the question is, can this matrix be the identity? Well, the answer is no, but let's think about why, or let's justify this answer. So let's focus here on matrix B. It is 3x4. We have 3 rows and 4 columns. The rank of B must be less than or equal to 3 because we have no more than one leading one in each row. And with 4 possible columns, that says that the nullity, this is the rank nullity theorem, the nullity or the dimension of the kernel of B must be bigger than or equal to 1. Okay? Now, therefore, there exists an x not equal to 0 such that if we take b times x, we get 0, right? This vector x is in fact in the kernel of B. Well, let's just multiply. If we take this particular vector x and we take AB times x, so first I'm thinking about it like this. Matrix AB times x, but there is an associativity here, so I can write this as A times BX. BX is 0, so this is A times 0, and any matrix times the 0 vector gives us 0. Now, what have I justified? This shows that this particular vector x is in the kernel of this product AB. We have a non-zero vector in the kernel of A times B. It cannot be the identity. Therefore, because the kernel of the identity is 0. Okay, so this completes this answer and this justification, but I want to make a comment because I'm going to do something more general next that's, well, more powerful than this. I want to make a comment as to what we actually showed or could show using the exact same argument, and that is as follows. What we did is we took an element in the kernel of B and showed that it's also in the kernel of AB. We, in fact, can, just through this argument, see that the kernel of matrix B, we take an element in that, and it's also an element in the kernel of AB. And so there is containment. And this symbol, it says every element in the kernel of B is in the kernel of AB. So I'm going to use this on the next the next page, but it's a good observation to make. And in fact, this came up in our homework a little bit earlier. So here is something much more powerful that I want to prove. And it's as follows. You have an n by p matrix A and a p by m matrix B. So we can immediately just notice that we can multiply A times B. And AB is n by m. Okay. But the statement is that the rank of the product is less than or equal to both the rank of A and the rank of B. Okay, so this is something you can use, and it's very powerful. In fact, we will do an example right after this. It's very short, just using this theorem. But let's prove it. So first of all, we will prove one. So first, I need to make a claim. This also was in homework, but for the purposes of this video, I will justify it here too. My claim, the image of AB is contained in the image of A. In fact, once we have this, then we can justify one almost immediately. So to prove the claim, well, this is about containment. So we just let Y be in the image of this product. Okay, so what does this mean? Then there exists vector x with AB times x equals y. This is what it means to be in the image. There is some vector that maps to this vector y. Well, again, I can just group things differently. So first, I'm thinking about this, right? AB times x is y. We see, just group it differently. We have A, and then group this, bx. This, again, is associativity, equals y. And so we have found a vector here. This is a vector such that A times that vector is y. This shows, so therefore, y is in the image of A, right? Because here's the vector. Bx is a vector such that A times that vector is y. Okay, so this proves my claim that the image of A is, the image of AB is contained in the image of A. Now, how do I get the first part of this theorem using this claim? Image of AB is a subspace, and it sits inside this subspace, which is the image of A. So if we think about the dimension, because the rank of this product is the dimension of the image of AB, and the image of AB sits inside the image of A. So for instance, this dimension must be less than or equal to the dimension of the image of A. You could see that just by, to get a basis for the image of A, just start with the basis for the image of AB, and then you might have to add some things to fill out all of a basis for the image of A, for example. That's how we get this less than or equal to. And this one is the rank of A. And so you see, we get exactly what we were hoping to see here. The rank of AB is less than or equal to the rank of A. Here's the less than or equal to. Okay, this is the end of number one. Now, here comes number two. And this is really where we need to use the rank nullity theorem. So to prove number two, the rank of AB is less than or equal to the rank of B, I'm going to back up just for a moment. You see the kernel of B, maybe I should copy and paste this. We made this observation, and I did this intentionally. Copy and paste. So we have that the kernel of B is contained in the kernel of AB. Now, the dimension of the kernel of B is the nullity, right, of B. And the dimension of the kernel of AB is the nullity of AB. Therefore, the nullity of B is less than or equal to the nullity of AB. Right? Fantastic. Well, we're trying to say something about the rank. But if you think about this, what is the number of columns of the product? It's here. The number of columns of AB is M, and the number of columns of matrix B is here. Okay, it's also M. So we can use the rank nullity theorem. The rank of, say, B. This would be, by the rank nullity theorem, this is M minus the nullity of B. Now I'm going to have an inequality here. I am going to replace this with the nullity of AB. So if you subtract off something bigger, it goes this way. This is greater than or equal to. I'm subtracting off something bigger, which is the nullity of the product, A times B. And then, because AB has M columns, this is precisely the rank of AB. And so you see what we get. In fact, we have finished this proof because, look, we have the rank of B greater than or equal to the rank of AB. And that's precisely number 2. So this is something quite fascinating and quite powerful, and it comes directly, really, from the rank nullity theorem, right? So we have shown anytime you have two matrices such that the matrix product is defined, then the rank of AB is less than or equal to the rank of A and less than or equal to the rank of B, okay? So once we have this theorem, we can use it. So I want to do an example that's actually very similar to the first one we did. Similar to this one, but our justification will be much shorter, just using arguments about rank. And that's here. Suppose we have a 5x4 matrix A and a 4x5 matrix B. We want to show the product AB cannot be invertible. Certainly the product AB is defined. It is 5x5, right? We have a 4, we make the product 5x5. But you notice, because of the sizes, the rank of A will be less than or equal to 4 because we only have 4 columns. And similarly, the rank of B will be less than or equal to 4 because we only have 4 rows. And so by this theorem, which we just proved, and like I mentioned, it came directly from rank nullity theorem, the rank of the product must be less than or equal to, well, both of these. So the smallest of the two, for instance, which is 4. And in particular, that says that AB is not invertible because we know invertible, a 5x5 invertible matrix will have rank 5. And this is the end of this example. You see it's shorter using this powerful theorem that says the rank of a product is less than or equal to the rank of each individual matrix. Thank you.